here in the quantum devices, as we know, the path to ever smaller geometry devices involves unique active devices which makes practical use of quantum mechanical principle. So, as physical geometry becomes very small, electrons may be treated as the quantum mechanical equivalent like a wave. So, devices making use of quantum mechanical principle include the resonant tunneling diode, quantum tunneling transistor, metal insulator metal diode and quantum dot transistors. These are the some of the basic electronic devices which use the quantum mechanics, and these are more practical devices, and these are active devices, smaller geometry devices, and using the quantum tunneling process. So, quantum tunneling, once we discuss about the quantum tunneling, then we will be able to understand these devices easily. So, quantum tunneling is a passing of the electron through an insulating barrier which is thin compared to the de Broglie electron wavelength. So, that is why it is possible to tunnel the electron from one potential well to the another potential well. So, it is passing of the electrons through an insulating barrier which is thin compared to the de Broglie electron wavelength. If the electron wave is large compared to the barrier, there is a possibility that the wave appears on both the side of the barrier. So, you can see from this classical view of an electron surmounting a barrier or not. Quantum mechanical view allows an electron to tunnel through a barrier. So, this probability is related to the barrier thickness. Now, you can see easily on the screen left hand side we are having a classical view. Energy, you can see here energy versus potential. So, now the right hand side you can see there is a quantum mechanical view, and through the green curve you can see that there is a probability just to cross the barrier which depend upon the thickness of the barrier. So, you can see easily that how the electron are tunneling from the left hand side and right hand side as the barrier thickness is less. So, it is very easily just it will be on the both the side of the tunnel. So, quantum mechanics allows for a probability of the electron being on the both the side of the barrier. If treated as a wave, the electron may look quite large compared to the thickness of the barrier. Even when treated as a wave, there is only a small probability that it will be found on the other side of the thick barrier. As you can see, it is very difficult to find at the thick barrier, but at the thin barrier we can easily find it. See the green portion of the curve, so figure above define the thinning the barrier, increasing the probability that the electron is found on the both the side of the barrier. The right hand side diagram is representing this phenomena. So, tunnel diode, if we talk about in a conventional electronics, so tunnel diode, the unqualified term, the tunnel diode referred to as a tunnel diode and early quantum devices. So, a reverse bias diode forms a depletion region and an insulating region between the conductive anode and the cathode. So, the depletion region is only the thin as compared to the electron wavelength. When heavily doped, that will be the 1000 times the doping of the rectifier diode. With the proper biasing, quantum tunneling is possible. Now, another device is the resonant tunneling diode. That resonant tunneling diode is a quantum device, not to be confused with the tunnel diode. Conventional heavily doped bipolar semiconductor, but this having the electrons tunnel through two barriers separated by a well inflowing source to the drain in a resonant tunneling diode. Electron tunnel through the two barriers that is separated by a wall and in the flowing the source to drain in the resonant tunnel diode. So, tunneling is also known as the quantum mechanical tunneling. So, the flow of electron is controlled by the diode bias. So, this matches the energy level of the electron in the source to the quantized level in the well, so that the electrons can tunnel through the barrier. So, there must be a matches the energy levels of the electrons in the source to the quantized level in the well. So, the energy level in the well is quantized because the well is small. When the energy level are equal, resonance will occur that allow the electron flow through the barrier, as we have seen in the diagram. So, no biased or too much biased, or similarly it yield a energy mismatch between the source and the well, and there will be a no conduction. So, this is the resonant tunneling diodes energy level diagram. So, we will discuss one by one. First is the no bias source and well energy levels not matched. You can see here that this well is made with the various materials. You can see here the gallium arsenide, indium gallium arsenide, aluminum arsenide. So, these are the combinational bands it is prepared. So, no bias source and the well energy levels are matched. You can see through the red line, these are not the matched energy. Another, the small biased causes matched energy levels, resonance conduction result. So, there is a matched energy level, you can see the energy levels in the red. So, because of the small biasing, these energy levels are matched. The previously these are not matched when there is no biasing. When the small biasing, these are the that causes the matched energy levels. Another is the further the biased mismatch energy levels decreasing conduction. Now, here the conduction results, resonance will take place here, but now again the further bias mismatch the energy levels and the decreasing conduction. So, as the bias is increased from 0 across the RTD, the current increases and then decreases corresponding to off and on and off end states. So, this makes simplification of the conventional transistor circuits possible by substituting a pair of RTD for two transistor. RTD means we are just preparing the resonance tunneling diode. So, for example, two back-to-back RTD and a transistor form a memory cell, which using the fewer component, less area and power compared with a conventional circuit. So, what is the use of RTD? It is it is a smaller device and using the fewer component as well as having the less area, power compared with the having the less power as compared to the conventional circuit. So, the potential application of RTDs is to reduce the component count, area and the power dissipation of the conventional transistor circuit by replacing some through not all transistors. By replacing transistors, we can make this RTD system. So, RTD have been shown to oscillate up to 712 gigahertz. So, now another device is the double layer tunneling transistor, that is also known as a DELT. that is double layer tunneling transistor is also a quantum device. So, DELT, otherwise known as a double layer tunneling transistor, and is constructed of a pair of conductive wells separated by an insulator or high band gap semiconductor. So, we can see in the figure that we are having it is just constructed by a pair of conductive wells that are separated by insulator or the high band gap semiconductors. So, this well are so thin that electrons are confined to two dimensions. So, these are known as the quantum wells. So, a pair of these quantum wells are insulated by a thin aluminum arsenide, which is having the high band gap, and it does not easily conduct layer. So, electrons can tunnel through the insulating layer, and if the electron in the two quantum wells have the same momentum and the energy. So, the well are so thin that the electrons may be treated as a wave and the quantum mechanical duality of the particle and wave is possible. So, the top and the optional bottom control gates may be adjusted to equalize the energy level resonance of the electron to allow conduction from the source to drain. So, barrier diagram where we are having a red bar, which you can see here, there is a red bar which can be defined the top quantum well contact, and left hand side we are having the bottom quantum contact that is the drain. Both the side we are having a drain, and the top gate and the bottom gate, you can see that is also the red color, and here we are having a bottom depletion gate. Moreover, there is a top depletion gate. The source is there, source and the drain here we are working with. So, these are the material which is gallium aluminum arsenide and insulator that is in between the two source, you can see here in the white line. So, there is a tunneling process takes place. So, that at left hand side you can see there is a well and there is a barrier. Well is the source where we are working and barrier is the insulator. So, how these electrons transfer these barrier and can tunnel through the insulator and just go to the another quantum well. You can see easily, it is a very easy diagram, it is very easily defined. So, this figure barrier diagram, red bar shows the unequal energy levels in the well, that is a off state condition. So, proper biasing of the gates equalizes the energy level of the electron in the well. So, the on state condition that will just equalizes the energy levels of the electron. Otherwise, at the off states, these are unequal energy levels in the well. So, the bars would be at the same level in the energy level diagram as it is on the on state. So, double layer tunneling transistors DELT is composed of the two electron containing wells separated by a non-conducting barrier. So, the gate voltage may be adjusted so that the energy and the momentum of the electrons in the wells are equal, which permits the electron to tunnel through the non-conductive barrier. So, the energy level are shown as unequal in the barrier diagram because there is a there is the off state. So, if the gate bias is increased beyond the required for the tunneling, the energy levels in the quantum wells are no longer matched. Tunneling is inhibited, source to the drain current decreases. So, to summarize, increasing gate bias from 0 result is on, off, on conditions. This allows a pair of delts to be stacked in a manner of the CMOS complementary pair. Though different P and N type transistors are not required, power supply voltage is about 100 milliwatt. So, experimental DELT have been produced which operates near the 4.2 K, 77 K and the 0 degree K. Room temperature version are expected. So, we just require at the room temperature so that this DELT can work. Now, another is the MIM diode, that is the metal insulator metal, that is the one of the quantum device that also based upon the quantum tunneling process. So, MIM diode, that is a metal insulator metal. Diode is a quantum tunneling device not based on the semiconductor. This is the quantum tunneling device. So, MIMS diode we can see in the diagram. This is the metal, you can see MIMS diode left hand side, right. Now, again we discuss when is the biased, when is the less biased and when will we are having the more biased. So, the insulator layers must be thin as compared to the de Broglie electron wavelength for the quantum tunneling to be possible. So, this is very clear for all the quantum devices that the insulating layer which we are using must be thin as compared to the conventional diodes. So, here the insulating layer must be the thin compared to the de Broglie electron wavelength. So, for diode action there must be a preferred tunneling direction resulting in the sharp bend in the diode forward characteristics curve. So, the MIM diode has a sharper forward curve than the metal insulator metal diode. So, you can see here the metal insulator diode, that is MIM diode. There is a cross section of the diode, energy level for the no biasing, forward biasing and the reverse biasing. Now, first there is a no biasing, you can see the metal M1 and M2 are at the same level, but I2 and I1 not at the same level, but these are the thinner as compared to the metal. So, another that you can see here, that is a forward left hand side and the right hand side it is the reversed bias. You can see here the M2 is very less, energy level of the M2 is less as compared to the M1, and there is a quantum well, that is a tunneling process takes place, and on the right hand side reverse, this is the reverse biased, it is also the M1 is now having the lesser energy band as compared to the M2. Now, the energy levels of M1 and M2 are equal in the no bias, that is very clear, we have seen in the figure. However, the thermal electrons cannot flow due to the high L1 and L2 barrier. So, there is a, you can see here that the I1 and I2 are having the high level. So, there is a not possible to flow of the electron. So, electron in the metal M2 have a higher energy level in the reverse biased. We have seen that M2 here is the higher as in the reverse bias, but in the forward bias M1 is higher. So, higher energy level in the reverse bias, but still cannot overcome the insulator barrier. So, if forward bias is increased, a quantum well, an area where the electrons may exist is formed between the insulator. So, electron may pass through the insulator L1 if M1 biased is at the same energy level as the quantum well. Now we can see here that this is at the M1 is at the same energy level of this insulator I1 and this insulator L2. Now this is possible condition where the tunneling will be possible. So a simple explanation is that the distance through the insulator is shorter. Now the electrons may pass through the insulator I1 if M1 is based on the same energy level as the quantum well. A simple explanation is that the distance through the insulator is shorter. A longer explanation is that as the bias increased, the probability of the electron wave overlapping from M1 to the quantum well increases. For the more detailed explanation, we can further go through this devices. So, MIM devices operate at a higher frequency, that is a 3.7 terahertz than microwave transitions. So, the addition of the third electrode to the MIM diode produces a transistor, right. So, these are the quantum devices which based upon the quantum tunneling process. Another device is the quantum dot transistor. So, quantum dot transistor is an isolated conductor may take on a charge measured in coulombs for large object. So, for a non-nanoscale isolated conductor known as a quantum dot. Whenever we talk about the nanoscale detection, so we use a quantum dot. So, for a nanoscale isolated conductor is the quantum dot. The charge is measured in the electron. Now, the quantum dot of 1 to 3 nanometer may take on an incremental charge of single electron. So, this is basis of the quantum dot transistor and also known as the single electron transistor. This is the beauty of this transistor, that it can measure the 1 to 3 nanometer and moreover of a single electron charge can be measured through this quantum dot transistor. So, a quantum dot placed adopt a thin insulator over an electron rich source which is known as a single electron box. So, the energy required to transfer an electron is related to the size of the dot and the number of electrons already on the dot. So, a gate electrode above the quantum dot can adjust the energy level of the dot, so that quantum mechanical tunneling of an electron from the source through the insulator is possible. So, the single electron tunnel to the dot. So, that we can see here, that first is the not biased, another is the biased. You can see that there is a possibility of the tunneling. You can see here from source to insulator there is a possibility of tunneling. Tunneling start in the diagram B and finally in the C we are having the tunneling. So, a single electron box and insulator quantum separated from an electron source by an insulator. You can see here the quantum dot source and insulating are different. So, another positive charge on the gate polarizes quantum dot, tunneling an electron from the source to the dot, tunneling an electron from source to the dot. You can see here tunneling, this is the first where we are having a single electron box and isolated quantum dot which is separated from an electron source by an insulator. You can see here that this is a source and insulator and there is a gate and then in between that there is a quantum dot and there is a tunnel barrier. Tunnel barrier basically is an insulator. So, positive charge on the gate polarizes quantum dot through which the positive charge which polarizes the quantum dot, and now tunneling an electron from the source to the dot. Now it is possible. Now third, quantum transistor, it means that the channel is replaced by the quantum dot and surrounded by the tunneling barrier. You can see here there is a barrier and this is the tunneling barrier. Now the quantum transistor which having the channel which channel of the quantum dot. Now if the quantum dot is surrounded by a tunnel barrier and the embedded between the source and drain of the conventional FET, the charge on the dot can modulate the flow of electron from source to the drain. So you can see here there is a flow of charge from source to the drain. It can be modulated through this tunnel. So now a gate voltage increases, the source to the drain current increases up to a point. A further increase in the gate voltage decreases drain current. So this is similar to the behavior of the RTD and the delta resonant devices. Only one kind of transistor is required to build a complementary logic gate. So this was the quantum dot transistor. So next is the single electron transistor, which is a pair of the conductors. Single electron transistor, if a pair of conductor, semiconductors, superconductors are separated by a pair of tunnel barriers, insulator surrounding a tiny conductive island like a quantum dot, the flow of single charge may be controlled by the gate. Where we are a single charge means a Cooper pair of the superconductors. So this is the single electron transistor similar to that, and which increases the charge on the gate, allows an electron to tunnel to the island. If it is the sufficiently small, the low capacitance will cause the dot potential to raise substantially due to the single electron. So no more electrons can tunnel to the island due to the electron charge. This is known as the Coulomb blockade. The electron which tunnel to the islands can tunnel to the drain. So a single electron transistor operates at near absolute zero. So the exception is the graphene single electron transistor having graphene island. This is called the experimental devices. So we are having a graphene transistor, also we are having a carbon nanotube transistor. So this graphene, we use the graphite as a allotropes of the carbon, does not have the rigid interlocking crystalline structure of the diamond. Nonetheless, it has a crystalline structure, one atom thick, so called the two-dimensional structure. So a graphite is a three-dimensional crystal, however, is cleaves into the thin sheet. So experimenters taking this to the extreme produce the micro size specks as the thin as a single atom, which is known as the graphene. So these membrane have unique electronic properties, highly conductive. Conduction is by either electrons or the holes without dropping of any kind. So graphene sheet may be cut into the transistor structure by lithographic techniques. So the transistor bear some resemblance of the MOSFET. So a gate capacity coupled to the graphene channel controls conditions. So a silicon transition scale to smaller size, leakage increased along with the power dissipation, and they get smaller every couple of years. So graphene transistor dissipate little power and they switch at high speed. Graphene might be a replacement of the silicon as it will work as more efficiently as compared to the silicon. So, graphene can be fashioned into the devices as small as 60 atoms wide. Graphene quantum dots within the transistor, this small serve as a single electron transistor, and this is the graphene single electron transistor uniquely function at the room temperature. So, graphene transistor are the first step production of the graphene by chemical vapor deposition have been accomplished on experimental scale. So, this graphene single sheet of graphite allotropes of the carbon we use. So, the atoms are arranged in the hexagon patterns with the carbon at each intersection, and the right hand side we are having a carbon nanotubes, a rolled sheet of the graphene. So, these are the 2D sheet of the graphene, and resulting the 1D is known as the carbon tube. So, we are having a 1D and 2D sheet which are used for the transistor. Further we will discuss in the next lecture. Thank you very much.